So good evening everyone. So myself Venkatesh, I am coming from IIT Hyderabad, and my team member Dr. R. Kannan, he is from National Institute of Ocean Technology, and on behalf of my team, I will be presenting the slides, and we will be presenting on adaptive neural networks for single channel speech enhancement. So I will be talking about neural networks mostly. So please bear with me if you don't know like deep learning and all. Okay. So this will be like overview kind of thing. I will not be talking about any architecture or anything. So it's just like the idea that I'm trying to present, and like how we can. So mostly I'll present an idea from image processing and how I wanted to take it to speech. Okay. So that's my goal. So yeah. Coming to the motivation, so like we are trying to look at the adaptive neural networks for a single channel speech enhancement. I mean the adaptive in the sense we wanted to change the neural network based on the input. For example, if we see the current neural networks, once we train the neural network, we keep the network fixed, and for any kind of input we use the same network to enhance the signal, right. So like if like we trained on a certain amount of data, so based on the availability of data, we trained on certain amount of data, and we will not be able to cover all the data that we have in the world, right. So we will be missing some of the data, and like if we wanted to test it on a particular environment which we haven't trained, right. So if we wanted to test it on that particular environment, the model may not perform well, okay. So it may not perform well, it only performs better on the data that we have trained it on, right. So here we are trying to address the issue where we wanted to like change the model itself based on the input signal so that it performs better on any testing environment. Okay, so if we change the testing environment, we wanted to change the model itself. So the main motivation is coming from the adaptive filters. For example, if we take the steepest descent adaptive filter, the weights that we are using, it depends on the input. Okay, so like we change the adaptive filter at each time instant, and at each time instant, the filter weights are dependent on the input. Right. So if we see the weight update equation, so like the weights at the next time step, it is dependent on the current time step weights and also the input, right. So if the input is more correlated with the noise, I mean the error, then we have some information about the input in the error, and so we use the correlation, like the weight update will be directly proportional to the correlation of this input and the error. So when we don't have like any more information of the input in the error signal, we stop updating the weights. Okay, so that is the idea of steepest descent adaptive filter, and the main takeaway from this adaptive filter is that we wanted, like we are changing the weights depending on the input. So why can't we do it for neural networks also, right? So our idea is like current neural network models where the input is S of n, noise is speech signal, and d hat of n is the enhanced signal. So we use a fixed f which is representing a neural network here, and we wanted to change it based on the input. So now I am making it a function of s, right. So that is the change that we wanted to make, and like how we can do this, that is the question that we are asking. And one way to do this that I will be discussing here is test time training. Okay, so during testing we will train the network again. Okay, so we change the parameters. So how many parameters to change, how to change the parameters, those are the things that I am going to discuss about in this particular presentation. Okay, and like this particular paper that has been published in like PMLR 2020, which is one of like prominent conference on like the machine learning. So we'll be discussing this particular paper, and we'll also like end it with some remarks on how we can use this for speech enhancement, right. So yeah, so coming to the test time training, so the main idea is that like the test sample that we are having from a test environment, it gives us a hint about like what the test environment is, right. So single test sample, which is sample from a like the random process, it gives us a hint about the test environment. So now we wanted to make use of this test environment, I mean the sample function from the test environment to update the network, right. So the model is no more fixed, we are changing the model based on the input, right. So we are changing it at the testing time. So like any neural network model, once we train it, we keep it fixed, but here we are changing it at the test time. Okay, so like like how we can change the network at the test time, right? So like for example, if you consider any neural network which is trained in a supervised manner where we have targets for particular inputs, so we train it by computing the loss and back propagating the gradients, right? So but for test sample we will not be having any target, right? So how we can compute the loss and how we can back propagate the gradients? So that is the question. So like to put it in simple words, we have the standard test error where we have x as input and y as output, and we compute the loss with respect to a particular loss function that we consider. For example, MSE we can consider, and we take the x minus y whole square and like we sum it over all the samples, and that is our loss function, and that is dependent on the network parameters theta, right? So that is our standard setup, and here in this paper they are proposing like changing the network itself, like the theta, by like we are using the input to change the network parameters. So that is the main idea. So and this we are doing it during the testing, so that we have to remember. So this is the algorithm. So like in standard setting, like we have the main task and we update the network parameters, minimize this particular loss function with respect to network parameters. We have to find the parameters that gives us the minimum loss, right? So that is our main supervised setting where we have actually the targets corresponding to the input. And now let us consider that we have a network with some number of layers, let's say k number of layers, and now like the algorithm is such that we fix a certain number of layers which will be shared across two tasks, right? So we will be having an auxiliary task where we update the parameters of the auxiliary task separately and the main task separately, right? So we will be having two different tasks, and the total parameters of the network will be halved, right? So like we will take certain number of layers which will be shared for main task and this auxiliary task, and we have separate heads for main task and the auxiliary task as well, right? So the first k layers, small k number of layers, we use it for like shared feature vector extractor, okay? So that is the shared part of the network, and for the auxiliary task we have separate set of parameters, and for the main task we have again separate set of parameters. I will show the block diagram so that you will get an idea. And now we carry out the training by minimizing two loss functions, right? So one is the main task loss and the other one is the self-supervised loss, right? So here the auxiliary task means that we are considering a self-supervised loss, okay? So since we don't have any targets for the test signals, we will consider a self-supervised loss, and we try to reduce the loss with respect to the self-supervised loss. So to put it in a simple block diagram, so we have this theta e which is shared between auxiliary task and the self-supervised main task, and for main task we have true targets, okay? So for example, if we are given an image of bird, our target is actually bird, okay? So that we know while training for any data set. But during testing, if we are getting some other picture which is not seen during training, we actually don't know what the actual target of that particular test sample is. So how do we find the loss with respect to like such kind of examples? We design a self-supervised task, right? So what kind of self-supervised task we can design? Like there are multiple number of self-supervised tasks that we can design. One example is that we can rotate the input image and try to predict how much rotation we have applied, okay? So this we are introducing, like we are getting the labels from the input itself. This we call it as self-supervised task. We get the labels from the input itself, right? So other than this, we can even like remove some parts of the input signal and we try to predict that particular part, okay? So we can remove like a block of the bird image and we try to predict that block. So that is called like self-supervised task. We are actually making the targets from the input itself. So we have now two tasks, one which is dependent on the labels and the other one which is not dependent on the labels, right? So we can compute it for any test sample, right? So now we train the network using these two losses, okay? So we combine the losses and we train the network using these two, right? So during testing we don't have any labels, so we don't have any loss coming from the main task, so that cross mark represents we don't have any label. And from the self-supervised task, even for any like any image that we are given during the testing time, we can like always rotate it and get the labels, right? So that is self-supervised task. We can always do that. and we can get the loss from that task always, right? So during testing, what we do is we compute the loss with respect to that particular head, right? And we back propagate it through theta e, right? So theta e is shared between both the self-supervised task and the main task. So we update theta e, and this updated theta e is used to compute the final output. Okay, so that updated theta e will be used to compute the theta, I mean the final, I mean whatever the class that we wanted to predict, we will predict it using the updated theta e. So that is the idea, right? So they are designing a self-supervised task along with the main task, where we can use self-supervised task during testing to update the network parameters, and that's where like the parameters of the network are dependent on the input now, right? So whatever the input is, like we update the parameters depending on the input, and now we use this updated parameters to compute the final class. So this is the main idea, and I don't wanted to talk about like all the results that they have presented in the paper because those might not be relevant for us. So I wanted to show some examples where it actually worked. So for example, this elephant image, the actual network which is fixed, it predicted it as dog. Okay, so that's where you see at the 0, like when we don't update any network parameters, at the 0th step it predicted it as dog. That's why like likelihood of that particular class is higher at 0th time step, and the likelihood of elephant is lower than dog. So like for any like if the network is predicting it as dog, like we will assign the label as dog for this particular example. And now if we update the gradients, right? So if we update the network parameters using the self-supervised task, you can see that the likelihood of the elephant is increasing, which means that the network is giving like correct label when we update the network parameters based on the input, right? So this is one very good example where they have shown like how many gradient steps we have to take to change this label from like dog to elephant. So this is what they are showing, and there are some negative examples also. Like first see positive examples. So like dog, after like using this kind of test time training, it predicted it correctly as elephant, and again like the other ones also. For example, the last one, which originally was predicted as car, and then after updating the parameters, it predicted as bus. But there are some negative examples also. But if you can see, like we cannot actually like predict the correct this one from the second, I mean the middle figure, right? So you can't really see snake there. So it's reasonable that it makes mistake there. Okay, so like when compared with the positive examples, the negative examples are more difficult, I can say, right? So that's what the test time training is. Now the question is how we can use it for speech enhancement, right? So the auxiliary task, so for the network to perform better on like any task, the auxiliary task that we are designing, those gradients has to be correlated with the main task gradients, right? So for example, if we take, in this case they are not directly correlated, so they haven't considered, like they are showing some gradient correlations, but so for any task to be successful, like the self-supervised task to help the main task, those gradients has to be correlated, right? So what kind of self-supervised task we can design for speech, right? So there are a lot of self-supervised tasks for speech to learn the representations, and there are mainly three different kinds of self-supervised representations, and we have contrastive self-supervised models where we take the model and we try to predict the immediate next samples, and we wanted to improve or increase the likelihood of predicting the next few samples, and we wanted to reduce the likelihood of predicting negative samples which are coming from a different utterance or something, right? So that kind of model is called contrastive loss, where we are trying to increase the contrast between predicting the next samples, immediate next samples, and reducing the likelihood of predicting the samples that are not coming from the same utterance. And we have predictive models where we try to predict the inputs. So for example, we can mask some of the inputs of the utterance, and we try to predict them using the network. So those kind of things are predictive models, and we have generative models where we are trying to generate the next few things, I mean next few samples of the utterance, right? So we where they are using variational autoencoders or things like that. So these are all okay. So but we don't know like which task we have to take, right? So as we have seen, like the gradients has to be correlated at the end, right? So now the question is why to go for this kind of self-supervised tasks which are not directly related to the input or the task that we are addressing, right? So we are addressing actual speech enhancement where we wanted to remove the noise from the speech signal. So what we can do is, and this is my idea, so we have this noisy signal and we add some more noise to this, right? So we add some more noise and we try to predict the noisy signal, right? So from the noisier signal, so where we have added some more noise to the signal, we try to predict the noisy signals. Now this particular task where we are trying to reduce the noise, we are not trying to reduce all the noise, but we are trying to reduce the noise that we have introduced explicitly, and this is kind of like reducing the noise only, and this gradients from this kind of auxiliary task will be correlated with the main task that we are addressing, right? So I think this particular task would be more correlated with this one. So these kind of models like noisier to noisy prediction, they have been explored like for self-supervised speech enhancement models, but at like in this kind of setup they haven't explored much, right? So like they haven't used it to change the network parameters during testing, right? So like we can now use this kind of task to update the network parameters based on the input signal, like if it is coming from like a different noisy environment than the one that we have trained on, we can update the network parameters and we can get the better estimate. But obviously the computational complexity will be higher because we are updating, we are actually taking a gradient step, right? So we have to compute a forward pass and then compute the gradients and take a backward pass. Whereas in actual testing time, we don't actually do this, we only do one forward pass. So actually the computational complexity is higher, but now we are not actually looking at the computational complexity, we are actually looking at how we can improve the performance even at the cost of computational complexity. And yeah, this is what I wanted to talk about. And any thoughts and suggestions? Okay.
Because there are different methods that to try to modify neural networks to work with voice, certain voice. Suppose that you want to tune the parameters so it will enhance a specific speaker with the same voice. Because maybe I use it all the time on my phone. So you want to modify it so it will adapt to my voice.
Personalized speech enhancement.
Yes, personal.
Yeah. So we can
also take that to that direction. Also, it's a nice extension.
does this make sense, sir? Like using
Yes. There are also some works on combining. So instead of using the large neural network, sometimes you want to use smaller neural networks, and you have training data. But instead of using the large training data, sometimes you have training data from a certain environment, but the noise, you don't have many examples, okay? So if you train the whole neural network, you train on all types of noise, and if you have many examples for one distribution, you will try to modify for this type of environment, okay? But suppose that there is another environment which is rare, but sometimes you have it. So you want to give a more weight to that environment. So you can split, instead of working with the loss function, which is the average of all the samples that you have, you can split it into classification, tensor
okay.
classification, and under this classification, you give more weight to the specific distribution that you have.
Okay.
So this is also related, things like that.
That is very interesting. And also like maybe all the noises or all the noise environments may require the full network. For example, if we have an input signal which is already kind of clean, so if we don't have to use the full network, we don't want to waste all the computational resources. We just wanted to use a part of network. But how to decide?
Yeah. So when you have a large variation in the training data, usually you need to increase the size, the number of parameters in the network. So you increase the network. But if you want to reduce it, so instead of, so you can split it into classifications. So there are many attempts to try to reduce the number of parameters, to reduce the size of the network. And then you want to train it such that it will perform well based on different environments. Because if there is a noisy environment here, maybe it remains. So the computational complexity for the classification is smaller because you classify it and then you remain in the same environment and then you work with these parameters. So all these works are related. Nice.
Any other questions or suggestions?
So who are the members of your team?
Uh,
Now please come over here.
Kanans. We just don't wanted to have any irregularities while presenting. So
analysis and our motivation using GCC fact, and then we're going to go to our explorations. We're still in the early stages, so yeah.
Basically, we are talking about a well-known application of phased array, that is like the direction of arrival estimation. So we are talking about a very common method and some challenges that when we really implement it. So it is basically for the speech localization, like to know the direction of source of the speech. So basically it involves two steps. You have to know the relative time difference of the arrival between the senses, that is the microphone, and you have to estimate the direction of arrival from the array configuration, like positions of the senses. So you can have two different models. Like coming to the problem setting, so another model that is more realistic is the real reverberant model. So that involves basically the multipath transmission, propagation, as well as like you have a reverberation, and it can be modeled like this, where there is this is the source signal, and the signal at each of the sensor is basically, you can model it as an as a filter, and you have the Gaussian noise added to this. So now onwards, talk about the actual.
So in generalized cross correlation methods, we basically find the cross correlation between signals coming from recorded from a two microphone array. So the number of microphones is 2, and what we do is we take the time difference of arrival is the value that maximizes the cross correlation, and this is computed by taking the inverse Fourier transform of this term, which is a weighted cross spectrum here between the two signals. So the weight is this phi of f, and this is multiplied with the cross spectrum, and inverse Fourier transform is taken. So there are different choices for phi of f. So when we take it as 1, so the final signal reduces to be dependent on the magnitude of the signal. So this depends on the source signal, and it might interfere in the final computation. So when the second choice can be the inverse of the magnitude. So when this is taken, we can see that the time difference of arrival is in the phase term. So when we cancel out the magnitude, so we can get a peak at the time difference in the cross correlation plot. So the advantages of this is it is computationally efficient, and it induces short delays. But it is poor in when reverberation is high, because we considered the ideal free field model. So we are applying this mostly to speech signal. So speech signal consists of different regions. It can be a voiced region. Voiced regions are generally periodic regions, which are like vowels. Unvoiced regions, these are consonants or fricatives, different parts of the speech which are non-periodic, and then silence regions. So these peaks, these parts like this, these are voiced regions, but these are small regions over here. You can see these are, but these are unvoiced regions, and this region here, this represents the silence regions. So we applied GCC FAT, or classical cross correlation, and GCC FAT on both periodic or voiced frame and an unvoiced frame. With classical cross correlation, this is the voiced frame, and this is an unvoiced frame or a fricative. So we can see that the peak is here, and when we subtract this with the maximum shift, we get the time difference of arrival. Same here, but you can see that in voiced frame there are different peaks. This is expected, so because the magnitude information is taken into account. But in GCC FAT we remove that magnitude part, so that there is only one peak here. So the challenges is GCC FAT or classical cross correlation. It's poor in highly noisy environments. It moderately noisy and noisy environments it performs well, but it fails in when room reverberation is high. So we thought, can we use the information present in the log magnitude spectrum, or these two have different characteristics, the voiced and the unvoiced frame. Our analysis is basically mostly on the voiced frame. So we can see that there are multiple peaks here in the voiced frame, and can we explore this information, additional information in the voiced frame to come up with a time difference of arrival. So I've taken two frames of voiced frame, which is shifted. This is simulated, but you can see that so we are considering a method called zero frequency filtering. What it does is it tries to identify glottal closure instants where voice frames, how they are produced is when the vocal folds in the glottis, they vibrate, and the periodic puffs of air are produced, and the vocal tract shapes them and gives the voice frame as output. But so zero frequency filtering identifies these points of glottal closure. So we get peaks like this at glottal closure instant, which gives the pitch or the excitation information. So if we take this from the two frames, the shift from microphone 1 and the microphone 2, and when we compare, we get this peaks like this, and when we subtract this, we'll get the time difference of arrival. So this was the initial exploration and initial idea. So this initial testing shows that for this frame, for one frame, it still gives the peak relatively well, even at minus 10 dB SNR. We are still to test it. We are still yet to test it on more varied data like many speakers, many languages, or more noisy, more reverberant cases. But this is just simulated, and yeah, we are able to estimate the time difference of arrival with this case. So this we're still in exploratory stage. So yeah, if you have any questions or any suggestions.
You know that just comment. There is what is called for the direction of arrival. You know, maybe you did already. With the other methods, which are there is we have the steering method, which extract the maximum power. So instead of using two sensors, just to estimate the time of arrival. Also the music and related methods. So work on all methods, not just these methods, because it's suboptimal to find the triangular arrival between any pair, and then to find the direction. Okay? But you can do some estimation of the direction using all the sensor at the same time. Just to be familiar with it.
Yeah.
I don't know if you work on it. Nice presentation. If it's just within the course, if you want to extend and work on it, there are many methods.
Thank you.
Yeah, I'm Tarun Teja. They are PG students from NIT. They are unable to attend today's. So I'll be talking about the underwater communication challenges and where our mathematical foundations on signal processing and array processing will be of useful. I'll be talking about the underwater communication as well as sub-seabed multi-beam sonar, which we are working on. So underwater wireless communication challenges. Underwater channel is time varying multipath in nature, and it has Doppler shift because the channel itself is dynamic, and the vessels or the submersibles, whichever is in the ocean, they are also in moving condition. So it has a Doppler shift, and underwater channel has limited and range dependent bandwidth. So if we want to communicate very long distance, we have to go for low frequencies. And if we are going for low frequencies means very limited bandwidth availability. So we will be able to communicate less number of bits information only. And underwater channel is of low propagation speed. The speed is around 1500 meters per second only. And also the channel has ambient noise. It's another constraint. So this is a typical scenario. So this has all the effects of the communication channel challenges. See, we will be communicating from the surface ship to the submersibles. So the surface side will have all the noise components present, the ambient noise and the noise made by. So communication between the ship and the submersible is the normal communication we use. So, and in the surface side only, all noises will be present, ambient noise, the noise due to wind, waves, bubbles, all those noise. And then the man-made noise, ship noise, all other noise are part of the surface side. When we go deeper, actually the noise component is lesser only. So here we have multipath components. So the signal, whatever we are sending or receiving, they will actually undergo many paths, reflections from surface, seabed, all these things, and the resultant is a combination of all signals. So this is actually the multipath time varying transfer function. So this will undergo all this transfer function. And because of this motion between the two vessels, we have the Doppler effect. So it is very difficult to reconstruct the signal. In this underwater communication, if we want to recover the data, then we have to reconstruct the signal at the receiver. So reconstruction means then the distortion should be less. So we need to choose a filter which is suitable, which will have less distortion. So that is one of the inference. And then also we can use more than one sensor in the receiver side so that we can have more SNR in the receiver side, which will improve our SNR. So this is another inference what we have. So another topic where we are working on is the subseabed beamforming sonar. So this is actually our array configuration, the projector array and the receiver array. The footpath of this projector array will be like this. This is yellow color. And the footpath of this receiver array is like this. And the intersection of these two is our region of interest. So we will be pinging. One ping will be made by the transmitter array. So this area will be enzonified. And the all receiver hydrophones will receive information from all these enzonified area. And based on the beamforming angle, only that area will be of interest, and then that signal alone will be improved with the SNR, and we will be able to get a good SNR in that position. So the beam will be steered all along this transmitted path. So with this configuration, this is how this beam steering is being done. We have used delay sum beamforming, and this is the del R, and the del R is d sine theta, and here we have considered this as the theta, and these are the number of sensors. So and in a phase representation it is 2 pi d with sine theta by lambda, and this is the summation of signal of the beam formed signal. So based on this, we just conducted one experiment in Bay of Bengal. This is the transmitter array 1 by 6, and this is the receiver array 1 by 16, and this is the tow body, and this is the receiver array. You can see this is the transmitter array. This is actually Mills cross array configuration, you can see. So with this we got the images of a shipwreck which was in the which was already in the Bay of Bengal. This is the depth profile, and this is the beam formed information, scanned information across track, and this is the elevation information of the scanned information. And this is another picture. So this highlighted information is from this object which is buried around 3.5 meters below the seabed. So that we are able to identify, and then we are able to find the dimension of that object. So this we have experimentally done, and then we are actually in the process of enhancing the signal to noise ratio and improving the system. So this course is very much useful for applying all the concepts whatever we have learnt, and then we will be make use of this performance enhancement for this. Thank you. So, any questions, sir? Okay, sir.
I am Rajeshwari from National Institute of Ocean Technology, Chennai. My team members, K. Triveni, she is a research scholar in NIT Warangal, and Kiran Deepthi, she is a BTech student. So we are going to discuss about the topic direction of arrival. So the problem statement is using music algorithm. So music is nothing but it's an acronym. It's a multiple signal classification. There are many algorithms for estimation of direction of arrival. In this talk we are going to discuss about music algorithm. Why we chose this algorithm is it is easier to implement in hardware. That's why we chose this music algorithm. So where it is applied, this DOA where we can apply is it is mainly used for this radars and sonars. Many applications it has, as earlier people discussed. So what are all the challenges present in this music algorithm? We can resolve the angle of arrival very precisely, and that is one advantage. And one more issue what we face is how to keep the elements, the spacing between the two elements. So that is another challenge we face. This is actually one source and multiple linear array of sensors we are having. In our analysis, what we have done is we have taken an array, a linear array of sensor, various elements we have taken around 18 elements, then 10 elements and 4 elements. By varying the number of elements, how it will have a performance on the output, that we will show. The basically how music algorithm performs is, first we receive the signal from the array, then we do the covariance. First we find the covariance, we do the signal decomposition, then we find the steering, we find the product of the steering vector multiplied by the noise space, and then we find the norm of that. It's a reciprocal of that. So that will give a peak whenever the direction of array, if a signal is present in that particular direction, we will get a peak signal. So first we are showing just a signal, a burst signal we have taken, of length 300 samples. This figure 2, what it represents is we have assumed two sources coming from two different directions. So why it is overlapped is, actually we have given a delay between two sensors. That is why in between from 100 to, actually it is blank from 0 to 100, and from 100 to 400 signal 1 is present, and from 300 to 600 another signal is present. So both we have added physically, we have added, and this is a DOA for 18 elements. We have simulated for a direction from 65 degree and 75 degree. We can the number of elements we used is around 18 elements. So we can see for the when the number of elements reduces, what happens. So you can see a split in between the two peaks. So that means the number of elements are not sufficient, or still if it is closer you will not be able to resolve it. And then the next case is we are having 4 elements. See, both signals from two directions are merged. We are unable to resolve. So from this what we can understand is the number of elements. First we want to find out what is the resolution we require. So based on that the number of elements need to be determined. Then what is the spacing also we need to find out. How much, what is the frequency of operation, and what will be the element spacing. That both are important. That's all. Thank you very much. Yes, sir. Thank you very much, sir.
To submarine radiated signal enhancement, and my name is S. Vidyarani from NIT Warangal, and my team members are Fabim Ibrahim from NPOL and Hepzibah from LBRIT. So
we have selected a topic which is based on single channel signal enhancement. Our aim is this problem is of practical importance. We have not done any simulation, we have just formulated the problem. We have signal radiated from the submarine. It is picked by a single hydrophone which is deployed underwater, and the signal will be transmitted to some air platform or a ship-based platform. Aim is to enhance the submarine radiated signal. we can model the received signal as sum of the submarine radiated signal plus the noise. The hydrophone, which is a sensor, is designed in such a way that the self noise of the hydrophone is much lower compared to the complex environment, that is ambient noise. So the challenges of the problem are that x of t is the signal that is radiated from the submarine, but we don't have the exact correlation matrix of the submarine radiated signal. We only know that the signal consists of discrete tonals plus a continuous spectrum. So the received signal is a sum of these two signals, but we don't know the exact frequencies or the spectral level. We don't know. We just know that it is of this nature. And related to ambient noise, we just know that ambient noise, that is the environmental noise, we just know that these signals, the spectrum folds off with the form 1 by f squared. At the time of measurement, we can measure the C state, that is at what is the level of the ambient noise. Among these curves, we can pick one curve. But we don't know exactly the correlation of the ambient noise also as a function of time. The challenges of the problem is that how do we enhance the signal using a single channel? Is it possible to enhance using a single channel? Or only using multiple channel is this signal enhancement possible? Obviously, conventional ways we can do a short time Fourier transform. A signal enhancement can happen, but this has a limitation that if the SNR of the signal is negative, we will not be able to enhance beyond the ambient noise. So we would like to, based on what we have studied here, we would like to explore whether we can apply Wiener filter and MVDR filter in this signal enhancement problem, whether it will degrade or enhance the signal compared to STFT. That's it. Thank you.